Good day and welcome back to the second part of our discussion on derivatives as a function. As indicated at the end of the previous video, we've reached that all-important part of our discussion on derivatives and their interpretations where it's necessary for you all to do some practice. And with that in mind, there is the associated class worksheet which you can find posted in Canvas along with the full typeset solutions. But of course, I'd also like to spend some time discussing a few of the problems. But if you have not taken the time, maybe 25 or so minutes, to work through these problems as much as you can, now would be the perfect opportunity to do so. So assuming that you've done so, I'm going to say something about problems 2 and 3b. So in problem 2, we're once again asked to find the derivative of a function. In this case, it's the square root of 1 plus 9x. So when we want to calculate the derivative, and at this point all we have at our disposal is the definition of the derivative, we go back to the limit of the difference quotient. So that would be the limit as h approaches 0 of f of x plus h minus f of x over h. And of course, by this point in time, you're very familiar with how I like to think about this composition. I think f of something is the square root of 1 plus 9 times that something. So whatever we substitute in for that something or that blank space, it goes into all of those blank spaces. So this would become the limit as h approaches 0. We're dividing by h. In the top we have the square root of 1 plus 9 times the quantity, x plus h. And we are subtracting away f of x, which is the square root of 1 plus 9x. And we find ourselves in this very familiar situation. We somehow need to use our techniques related to limits and eventually get to limit laws to evaluate the resulting limit. Note, we of course cannot simply plug in h equals 0. That would cause us to divide by 0. Instead, we need to do some type of manipulation. And when we've been in this scenario in the past with the square roots present, the technique that we've used is to multiply by the conjugate over the conjugate. So I'm simply going to multiply by 1, in a somewhat fancy way. So we'll multiply by the square root of 1 plus 9 times x plus h plus the square root of 1 plus 9x. So the conjugate of what's in the numerator. And so that we don't change anything, we're going to divide by that same quantity so that we multiply by 1 and do not change the value of this limit. And kind of the quick reminder to the side and the reason conjugates are useful, if you have something like a minus b, which we do have, and we multiply it by its conjugate, a plus b, what we end up with is a difference of squares. So in this case, when we multiply out, it is going to look more involved, at least for a moment here, but it simplifies very nicely. In the denominator, we have the more complicated terms. We have h times its conjugate we multiplied by. And I'm going to go ahead and just for fun distribute that 9 through. And then in the top is where the nice cancellations occur. We get this first term squared minus the second term squared. A squared minus b squared. And if you don't see that, you could certainly, FOIL everything out. So we would have 1 plus 9x plus 9h minus the quantity 1 plus 9x. So when you square the square root term, the square roots vanish. Note that this minus sign does need to be distributed through, but when it is distributed through, you have a positive 1, a negative 1, plus 9x, minus 9x. And since we've seen these algebraic manipulations before, let's go ahead and immediately also note the h and the h now cancel. So this works out almost too good to be true. Right, you have the limit as h approaches 0. In the top you have 9. And in the bottom you have the square root of 1 plus 9x plus 9h plus the square root of 1 plus 9x. And we are now to that point where it makes sense, at least algebraically, to substitute in h equals 0. However, if we are going to do that, we need to correctly justify it mathematically. And unfortunately, the function we're dealing with is not a rational function, so we cannot use the substitution property. So a common mistake is to substitute in h equals 0. You end up getting the correct answer, but remember, the correct answer by incorrect means by no means will allow you to get full credit. So the observation that we want to make here is that we most definitely need to use the limit laws. And I'm okay with you doing a bunch of the limit laws at once. You can go ahead and say I need to take the limit of the top and divide by the limit in the bottom. Furthermore, I'm okay when you take the limit in the bottom, just breaking that limit up and even pushing it inside the square root of the first term. That indicates to me that you have thought about the fact that you need to use these limit laws. And remember, as we take the limit as h approaches 0, the 1 and the 9x and the 9 with respect to h are simply constants. So in the top, the limit of a constant is that constant. In the second term in the bottom, same idea. And in the first term, or first limit in the bottom, we have the limit of a polynomial in h. So you could take it further and use the limit laws, or you could justify that with the substitution property. And we end up with 9 over 2 square roots of 1 plus 9x. And just to tie everything together, we have f prime x is 9 over 2 square roots of 1 plus 9x, which completes the example. And now moving on to 3b from that class worksheet. We are given this limit as x approaches 0 of sine of x over x. And what we are told is that this represents f prime of a, so the derivative of some function f, at some numeric value a. And what we need to determine in this problem is what is a, what is f. And this really requires us to use a bit of pattern recognition. So typically we think of f prime of a to be the limit as h approaches 0 of the quantity f of a plus h minus f of a, all divided by h. And when it comes to evaluating limits, it's irrelevant kind of which variable, letter, symbol we use, as long as we have consistency. So we could certainly change this h into an x. So I really could think of this as being the limit as x approaches 0 of f of a plus x minus f of a over x. So in this case, if we compare back, we're thinking of this sine of x as being f of a plus x, and what we're subtracting away, a 0, would be f of a. And just by comparison, we should be able to immediately know what is f, what is a. So in this case, our function f of x is sine, and the a value is 0. And if there's any confusion whatsoever about this, just recall that f of 0 would be sine of 0, which is a common value we should be familiar with, 0. And furthermore, f of 0 plus x is sine of 0 plus x, which is just a sine of x, exactly what we have in that quantity. Let me also note that there's a different approach you could take as well. Recall that we previously have defined f prime of a as the limit as x approaches a of f of x minus f of a, all divide it by x minus a. And if you want to use this version of the limit and then in turn your pattern recognition, that certainly works as well. So two perfectly good ways to think about the same problem. So I highly encourage you to finish up the remaining problems on the worksheet, check versus the solutions provided on Canvas, and as usual, if you have questions, do not hesitate to reach out and make sure to practice suggested problems. Take care and stay tuned.